with nuclear gauges. But before going into safety, just what is a nuclear gauge? For our purposes, we'll use the term gauge or nuclear gauge to describe devices which use radiation to measure the level or density of a material during industrial processing. These devices normally consist of a source of radiation, radioactive material, which is placed on one side of the process container, and a detector placed on the other side. The material measured may be solid or liquid, and may be located in tanks, pipes, hoppers, or chutes, or on conveyors. But the main advantage of this type of gauge is that the measuring equipment does not have to touch the process material in order to do its job. This may be convenient for quality purposes in applications such as food processing, or crucial in other applications like steel or chemical production, where the process material, molten iron or hydrofluoric acid for instance, may be extremely hazardous. Now that we know what a gauge looks like and how it is used, it may be a little clearer why we need to talk about safety. Nuclear gauges rely on the use of radiation to operate, so in order to use them safely, it is important to understand some basic things about radiation. Let's start by defining radiation as energy traveling through space in the form of particles or waves. Wave-like radiation can take the form of familiar things like light or heat, or less familiar things, laser beams or microwaves, X-rays from the machine at the doctor's office, or gamma rays from radioactive materials. All of these are examples of electromagnetic radiation, which differ only in the amount of energy carried by each ray or photon. None of them can make anything else radioactive, but any of them can cause injury if encountered in excessive quantities. We distinguish X and gamma rays from the other types of electromagnetic radiation because they have special properties, like the ability to pass through solid materials. That something can penetrate through solids may seem both scary and exciting, definitely the stuff of science fiction, but it makes a lot more sense if you consider some basic facts about atoms. Back in high school, we learned that an atom contains a compact nucleus made of protons and neutrons, and that this core is surrounded by a swarm of orbiting particles called electrons. Viewed by something much smaller than the atom, it might look like a solar system, made up mostly of empty space. On this scale, solid objects don't look so solid after all. But let's say the viewer is larger, the same size as the atom or bigger. In that case, the spinning electrons would make the atom look more like a ball, and solid materials look pretty solid. Light rays and heat rays are big, like the second viewer. They tend to be blocked and bounce off of the atomic surfaces they encounter. Any energy transferred from these photons act to vibrate or heat entire atoms. X and gamma rays, on the other hand, are small, like the first viewer, and pass easily between the nucleus and the orbiting electrons. This accounts for their great penetrating power. But there is another property of X and gamma rays which sets them apart from other types of electromagnetic radiation. While an X or gamma ray is traveling through the empty space in an atom, there is a chance that it will encounter an orbiting electron. In this case, the photon may be absorbed and disappear, delivering some or all of its energy to the electron. If enough energy is delivered to the electron, it may be ejected from the atom altogether. This process is called ionization, and radiation, which is capable of causing this, is called ionizing radiation. The penetrating and ionizing properties of X and gamma rays are a dual-edged sword. These properties make them useful and cause them to be potentially hazardous. The penetrating property was first noticed by Wilhelm Röntgen when he discovered X-rays in 1895. He found that this new radiation passed easily through air and lightweight materials, but not so easily through heavier materials like iron and lead. He also found that he could use lead as a shield to block X-rays. The penetrating property of gamma rays allows nuclear gauges to be non-contacting. That is, because the rays pass through solid materials like tank walls, the gauge can be located outside of the process container. However, because of this same penetrating power, heavy shielding is needed for personal protection. The ionizing property allows the detection of the radiation at the opposite side of the tank or pipe. A signal is generated by the detector when ionization takes place inside it. This signal can be used to control processing equipment, such as valves or pumps, which keep the tank from overflowing or adjust the concentrations of input ingredients. Ionization can also cause damage if it occurs in biological systems like people. To understand how, let's take a closer look at the human body as a biological system. The human body is composed of trillions of individual cells made up of a variety of different kinds of molecules. The molecules can be as small as 2 atoms or as large as millions of atoms. Either way, the atoms are held together by chemical bonds. Chemical bonds are formed when the individual atoms share their orbital electrons. As we've seen, ionizing radiation can eject electrons from atoms. If the ejected electron was being shared in a bond between 2 atoms, then its removal would break the chemical bond and the molecule would come apart. It's the breaking of chemical bonds that we consider radiation damage. RNA and DNA are examples of extremely large molecules. Together, they are responsible for cell function and reproduction, so it is crucial that they remain intact. Their importance is reflected in the damage repair mechanisms which have developed over the course of human evolution. Specific enzymes have evolved which recognize breaks in DNA molecules and continuously repair the damage. The repair process has been measured as at least 99.9% efficient, so that only 1 in 1,000 breaks go unrepaired. But what about the ones that don't get repaired? What happens to them? Unrepaired damage to DNA can cause the cell to die, or can show up later as an increase in the risk of cancer or genetic defects. At this point, it's important to understand that you don't have to work with nuclear gauges or be X-rayed at the doctor's office to be exposed to ionizing radiation. We are all being exposed to this type of radiation all the time. Radioactive materials are present in the ground, in the material we use to build our houses, in the air we breathe, and even in the food we eat. In fact, we ourselves are measurably radioactive as a result of taking in small amounts of radioactive materials all during our lives. The radiation exposure we receive from these natural sources is called natural background radiation and is a continual source of exposure to everyone on the planet. So just how much exposure do we get from natural background radiation? Radiation exposures are commonly measured using a unit called a millirem. 1 millirem is a small amount of exposure and is about equal to the dose we all get each day from background radiation. The total background dose we get each year, then, is about 365 millirem. Of the natural sources mentioned earlier, the largest single contributor to our background dose is radon gas in the air we breathe. Radon gas gives each of us a dose of about 200 millirem per year. Other natural sources include cosmic radiation from the sun, which gives 30 millirem per year, foods, 40 millirem per year, and soil and housing materials, 30 millirem per year. Besides these natural sources, we all get an average of 50 millirem per year from medical sources and 10 millirem per year from consumer products like smoke detectors. The last 5 millirem per year comes from industrial uses of radioactive materials like nuclear power plants and processing plants. How does this compare to exposure on the job? In addition to background radiation, the average radiation worker in the nuclear power industry gets about 300 millirem per year, while it is estimated that the average gauge user gets only about 30 millirem. These average doses are well below the annual dose limit for radiation workers, which is 5,000 millirem. Now that we have some perspective, let's talk about high-dose effects. Radiation sickness occurs when the trunk of the body is exposed to doses over 100,000 millirem in only a few hours. Doses this high exceed the normal repair rate, and damage to DNA may cause cells to die in the process of cell division. Bone marrow cells, which produce red and white blood cells, are some of the most sensitive cells. When these cells die, the body is not able to replace the blood cells which were in circulation at the time of exposure. These cells naturally become old and ordinarily would be replaced with new cells. Symptoms of sickness occur in about 3 weeks after exposure, when the numbers of blood cells in circulation drop below critical levels. Infection and anemia can normally be treated medically until the bone marrow recovers and blood cell counts return to normal in about 6 weeks. The severity of illness and chances of full recovery depend on the dose. As the dose level increases, other organs, like the small intestines, are damaged, and the chances of survival are reduced. 1 million millirem is the maximum short-term dose that humans can be exposed to and still survive. All of these short-term effects are avoided by government-set dose limits, like the one mentioned earlier, and radiation protection program requirements. All right, so we won't see any short-term effects. But what about long-term effects, like cancer and genetic mutations? We all know that radiation causes cancer, right? Well, let's look at the facts. Adverse long-term effects, like cancer, have only actually been observed in groups of people exposed to large amounts of radiation. To date, no increase has been observed in the rate of genetic defects in any human study group exposed to radiation, including the children and grandchildren of Hiroshima and Nagasaki survivors. No new types of cancer or mutations have been observed as a result of radiation exposure in humans. All of the known effects observed were known before radiation was discovered. When radiation-induced cancers have been observed, they were only seen as an increase in the normal rate of that particular cancer in the general population. Finally, it takes a long time for cancer to develop as a result of radiation exposure. Leukemia, the first long-term effect to show up, still takes between 2 and 7 years after exposure to develop. Solid tumors aren't seen for at least 10 years, and normally not until 20 years following exposure. Such long periods allow time for potential exposure to many other carcinogens. This makes radiation extremely difficult to study as the cause of a particular cancer. We're not certain that there's any risk of long-term effects from occupational exposure. But, based on high-dose data, the risk of cancer death is estimated at about 1 chance in 2 million per millirem. This number can be compared to your natural risk of cancer death, which is about 1 in 5 for non-smokers and 1 in 4 for smokers. So, if a non-smoker were to receive a dose of 1,000 millirem, her chance of dying from cancer could increase from 0.2 to 0.2005. As you can see, this is a very small increase. However, to minimize this risk, many governments around the world have adopted a policy of ALARA regarding exposure to ionizing radiation. ALARA stands for as low as reasonably achievable. Under this policy, all exposures must be kept as far below the dose limits as practical, and unnecessary exposures must be avoided. Factors used to reduce worker exposures include limiting the amount of time spent near the source, maximizing the distance from the source to workers, and using shielding to reduce the dose rates everywhere except the useful beam. ALARA dictates that engineering controls must take precedence over administrative controls whenever practical, and several engineering controls have already been incorporated into the design of nuclear gauges. One simple engineering control is to use the smallest source practical. By small, we don't mean physically tiny. Radioactive sources are compared by their decay rates rather than their physical size. Decay rates are measured in units of disintegrations per second. A disintegration is said to have occurred when the nucleus of a radioactive atom expels its excess energy in the form of particles or waves, or both. One unit used to measure source size or strength is the Curie, named in honor of Marie and Pierre Curie, who isolated radium from pitchblende in 1898. One Curie, originally taken as the decay rate of 1 gram of radium, is equal to 37 billion disintegrations per second. This is a rather large amount of radioactivity by today's standards, and it's usually convenient to measure source strength in thousands or millicuries. Sources used in nuclear gauges range in size from about 50 millicuries up to about 8,000 millicuries, depending on the application. Sources are chosen so that the dose rate at the detector is only around 1 millirem per hour when the process material is absent or the tank is empty. These sources are typically 100 to 1,000 times weaker than those used by radiographers to check pipe and weld integrity. Once the source strength has been determined, the expected radiation levels and projected worker doses can be easily calculated. If the calculated doses are too high, steps can be taken to reduce the dose to the workers before any actual exposure occurs. The source capsule itself has been designed and tested to withstand extreme environmental conditions without breaking. The radioactive material is in the form of an insoluble ceramic or metal pellet designed to retain the radioactive isotope completely. The source pellet is placed within 2 stainless steel capsules, and the outer one is welded closed. Rigorous testing is then performed to ensure that no radioactive material will escape, even during a fire. The source capsule is placed in a lead shield, which is surrounded by a steel housing. Enough lead is used to reduce the radiation level 1 foot from the housing to less than 5 millirem per hour. In some cases, screened enclosures are installed to prevent personnel access to the radiation beam. In addition to these engineering controls, administrative controls are instituted at local plant sites, depending on what types and quantities of radioactive materials are being handled. Common administrative controls include quantity limits set by state or federal regulators, assignment of a radiation safety officer responsible for all activities involving radioactive materials, prior approval of planned work involving radioactive materials, written procedures, routine inventory, shutter test, and leak test for all gauges. locking the shutter closed when access to the beam path is required. Posting of signs identifying the presence of radioactive material. Maintenance of warning labels on the equipment. Training. Use of personnel dosimetry. And finally, regular program audits. If your job involves routine exposure to radiation, you are considered a radiation worker, and your annual dose limit is 5,000 millirem, or 500 millirem for declared pregnant women. What can radiation workers do to minimize their exposure to radiation? Ask for additional training on job-specific radiation safety. Be familiar with all procedures related to radiation at your facility. Strictly adhere to all postings requiring prior approval or lockouts involving radiation-related work. Be aware of the dose rates and potential exposures involved with your work. If dosimeters have been issued, wear them properly and keep track of your actual exposures. Close the shutter before working on the detector. Remove the electronics to the shop rather than working on them in place. And finally, ask your radiation safety officer for more information regarding the risk of occupational radiation exposure as published by the NRC. If your job doesn't involve routinely working with radiation, but you work at or visit locations where radioactive materials or X-ray machines are used, you are considered to be a member of the public, and your annual dose limit is 100 millirem. What can you do to minimize your exposure to radiation? Be aware of radiation postings in and around your work area. Don't spend unnecessary time near gauges or other sources of radiation. Ask your radiation safety officer for more information. Respect ionizing radiation like you respect electricity, laser beams, and microwaves. You can be confident that if you follow these simple precautions, your exposures will be well below those known to cause any harmful effects, while you and your company enjoy the full benefits of working safely with nuclear gauges.